Okay, we'll start our discussion. So, um, we have been talking about stability of linear systems for quite some time. We talked about the different notions of stability, and then we studied under what conditions would a linear system be stable. And so we had proved in previous class the following theorems. So I have x dot t equals to axt, and the equilibrium is x equals to 0 is the equilibrium. And in the last class, we proved the following result. I mean, we proved many things, but I'm just going to write the core result. X equals to 0 is stable if and only if sup t greater than equal to 0, phi t is finite, and then asymptotically or exponentially stable if and only if limit t goes to infinity, phi t equals to 0. Remember, phi t in this case is exponential of at. In the context of linear system, asymptotically stable is equivalent to exponential stability, but that's not the case for nonlinear systems. But we're talking about linear systems here. So for us, whether I say asymptotically stable or exponentially stable, or globally asymptotically stable or globally exponentially stable, it all means the same thing. All four things are equivalent in the context of uh, linear systems. And then we said that, look, I don't want to prove that exponential of at norm is bounded or exponential of at is going to 0. I want to have conditions on matrix A which allows me to infer stability and exponential stability. And so we talked about if real part of lambda I of A is less than 0 for all I, this implies exponential stability. If real part of lambda I A equals to 0 and it has an eigenvector and Vi is not equals to 0. What that means is that for each eigenvalue which has 0 real part, you have a unique eigenvector corresponding to that eigenvalue, then this is stable. So either the eigenvalues have to be, the real part has to be negative, or if the real part is 0, then you have a unique eigenvector corresponding to that eigenvalue. Then in that case, you have a stable system. Otherwise, the system is unstable, and you might have situations where for a given initial condition, the system might go to infinity. And I gave you the Everest example. So if you're standing on or maybe you are a good mountaineer, but I'm not. But if I'm standing on Mount Everest and I move like 1 inch in any of the sides, then I'll just fall. And that's the notion of instability. And so in that case, whatever dynamics I have, my eigenvalues have positive number. Like the real part of the eigenvalue will have positive value. Can someone tell me why systems are unstable? What leads the system to be unstable? So if I'm standing at Mount Everest, my kinetic energy is 0, my velocity is 0, my kinetic energy is 0, and I move like 1 inch, and then my kinetic energy becomes infinity or whatever, like it becomes very large. So where did that energy come from? Where did that kinetic energy come from? Yeah.
Because you could call it the potential energy of the state of the system.
Right. So the potential energy is not part of the state of the system, right? So because the velocity, my state contains, well, maybe you can infer the potential energy from the position of my body in the space. So in some sense you can, but okay, maybe then it's not a good example. A better example is, why does battery have thermal runaway and it explodes? Anyone wants to answer that? It's not part of the state of the system in that case, but it does lead to, there are situations where batteries become unstable. So where is that energy for instability coming from? Anyone has thoughts on it? You have some thoughts on it?
I know that's like a liner that melts.
Right, but why did that happen? Why does that happen in LA summer, LA downtown summer? You have a nice electric vehicle, $100,000 luxury electric vehicle, and it just explodes. By the way, something like that happened in Urbana-Champaign. So I studied at Urbana-Champaign. I subscribed to the news, and so I found that an electric vehicle spontaneously caught fire and exploded in downtown Urbana-Champaign. Yeah.
So it may have to do with a certain state of the system which hasn't been realized when the system was being designed.
Not quite. For instability, for some states to go to infinity, some form of energy exchange is happening. So what's happening in that case?
I guess what it would be is the change in state is causing more and more of a response. You get more positive feedback loop.
Yes, it is. There is a positive feedback loop because of this explosion is happening. But where is that energy coming from? My question is about energy. Like, we know the laws of conservation of energy. So where is that energy coming from? So in the Mount Everest example, as you rightly pointed out, my state contains my information about my location, as a result of which there is the potential energy can be inferred from my state. But in the battery example, you cannot infer the potential energy. There's no potential energy there. So okay, I'll give you an answer. So it's actually chemical energy in the battery. So you put in that energy at the time of refinement. So when you are refining that particular lithium or whatever the chemicals are in the battery, you were refining it at some point of time, you injected energy into it, you put it in a state which is somewhat unstable, and then you put it in a battery pack, and you added all this membrane and control and all that stuff in order to make sure that it is stable. But if the temperature of the battery pack goes above a certain limit, so you are in downtown LA, your ground parking lot asphalt is probably at, in the peak summer, it might be at 110, 120 degrees Celsius. No, maybe not that much, but pretty high. And so the battery pack is absorbing all that energy from the road surface, and then it's, at some point of time, the thermal runaway happens. What that means is that the chemical energy stored in the battery converts into this explosion that you see, which is more of a chemical explosion. And so the instability that you see, so if temperature is the state that you are measuring, you weren't quite in the unstable domain, but because of the environmental condition, it pushed it into the unstable domain, and then the temperature rose to infinity. And the temperature rose to infinity purely because there was chemical energy in the battery that converted into thermal energy at some point of time. So whenever you see instability, there is some form of energy changing from one state to another. Sometimes that energy can be inferred from the state, as was the case in the Mount Everest example. Sometimes that energy cannot be inferred from the state because you're not really measuring that as in your equation, in your state equation. Okay. So what are we going to do today? So we talked about the stability from the exponential of AT point of view. We talked about stability from the eigenvalues of A point of view. Today I'm going to talk about Lyapunov stability. Lyapunov's direct method. It's called the second method or direct method. And this is from 1890s. I think it's 1892, but I could be off by a couple of years. So in 1890s, Lyapunov studied this thing and came up with a way to prove that a system is stable or unstable. So of course, Lyapunov's method can be applied to nonlinear systems as well. So right now we are going to talk about the context of linear system, but know that this method is way more general than what we are going to study in the class. So what is Lyapunov's method? So Lyapunov figured out that we can define something which is equivalent of an energy function. So I'm going to define an energy function. I'm overloading the operator V of x. So V is the energy function, the potential function. What is the property of this V of x? You can call it, I mean, most of the people would call it Lyapunov function today, but I haven't read Lyapunov's paper, so I don't know what Lyapunov was calling it, but I presume the idea was to think about a potential function around the equilibrium or energy function around the equilibrium. So I'm going to construct a function like this. This is my V of x. This is my x equilibrium. So in our case, x equilibrium is equal to 0. But as I mentioned, you can apply it in nonlinear systems. So you have some x equilibrium. You construct a function that is growing as you move away from x equilibrium. So that's my Lyapunov function. And what he wants to prove is d over dt v of xt is less than 0. So my dynamics is such that if I look at the time derivative of the Lyapunov function at xt, then it is negative, strictly negative. This is strictly negative. So if it is strictly negative, then what is happening? Okay. So I have an energy function around equilibrium, and the energy function is decreasing along the trajectory. So if energy is decreasing along the trajectory, what does that imply? It implies that xt is getting closer and closer to x equilibrium. That was his idea. Okay, that was his idea back in 1890s, and so that's what we want to prove. So we are going to characterize stability of the system with respect to the Lyapunov function, but we are looking at some specific class of Lyapunov function, which is quadratic functions, quadratic in x. Certainly you can have any positive definite function around x equilibrium, but in the context of linear system, quadratic kind of does the work that we want it to do. In nonlinear functions, nonlinear space, you can come up with more complicated potential functions or Lyapunov functions and show that this particular statement holds, and then it's stable. If this statement doesn't hold, if Vx is not positive definite around equilibrium, if it is not increasing in all directions around the equilibrium, then you may not have a stable system. So unstable systems would fail the Lyapunov test, as a result of which they are unstable. So we'll characterize the stability. We characterize the stability with respect to phi t. We characterize the stability with respect to eigenvalues of A. Now we will characterize the stability with respect to Lyapunov function. It's the I don't want to say increasing order of generality, but in my mind, this one and this one is similar because they follow from this exponential relationship. So I think of them as equivalent. This one, I think of it as more general because it can be applied to nonlinear systems as well. Okay. Let me, any questions so far before I jump onto the statement? Okay. Okay, so I'm given a dynamics. I want to construct a Lyapunov function such that this statement holds true. If this statement holds true, then I'm good to go. My system would be stable, and I'm going to prove that result. If this statement doesn't hold true, my system may be unstable. So let me start with the reason for Lyapunov function. So let me do a nonlinear system. So I have x dot of t equals to minus x cube t. So I have this system. I want to know if this system is stable or not stable. Okay, it's a nonlinear system. We haven't studied about stability of this system, but maybe in my dreams, Lyapunov came and said that, look, just come up with a positive definite function, come up with a Lyapunov function. What's the equilibrium here? What is x equilibrium? It's 0 because when x equals to 0, this term, the f of x, is equal to 0 as well. So x equilibrium is equal to 0. I'm going to define my Lyapunov function, v of x. Some Lyapunov function, the v is generally capital. I don't know if in the book v is small, but I know that v is also being used for eigenvectors. So just try to disambiguate the notation in your brain as you're going through this. So this v is Lyapunov function, and I'm going to define Lyapunov function as x square. Vx equals to x square. Okay, what is d over dt of v of xt? Can someone help me with this? What's a derivative of the value of the Lyapunov function at xt with respect to time? I'm taking the time derivative. So I'm going to use the chain rule. So dv over dx into dx over dt. This is evaluated at xt. This is evaluated at t. So what do I get? I get 2 times xt multiplied by negative x cube. So this is less than 0 for all x not equal to x equilibrium. So this implies globally stable. Do you see the power of Lyapunov's stability now? Lyapunov's second method or Lyapunov's direct method for stability. So the idea is to construct a positive definite function. I know that this is a positive definite function. This is greater than 0 for all x not at equilibrium. And it's actually increasing. It's going to infinity in all directions. And if I take the time derivative, my time derivative is strictly negative if my xt is not equal to x equilibrium. So as long as I'm away from the equilibrium, I am going to dissipate the energy in the Lyapunov function. Remember that I'm not talking, I'm using the word energy, but it doesn't really represent any energy in the system. It's just the way Lyapunov thought about it. And so we are thinking about it in the same way, and we are thinking of it as an energy, and then we are saying, look, the system seems to be dissipating energy as it progresses, and consequently the system is going to be globally stable. That was Lyapunov's method, and we are going to specialize this Lyapunov's method in the context of general linear system. Any questions on this side of the board? Is the motivation clear?
So
Yes.
how do we come up with that energy function? I don't know. It could be any other function which satisfies this particular condition.
So the only requirement for energy function is as you move away from equilibrium, it has to keep growing in both directions. I mean, in the context of linear system, it has to be positive definite. In the context of non-linear system, generally speaking, they are positive definite, but it need not be quadratic. It could be fourth order, or it could be sixth order polynomial, whatever makes sense for that specific system. Okay. Any other question? Okay. How do you come up with potential Lyapunov function? I think that's a very good question. We won't touch upon that topic in this class because for linear system, it's very easy to come up with Lyapunov function. For non-linear systems, you stare at the equation for 1 month and the Lyapunov function just pops out of the blackboard or whiteboard, whatever you're using to conceptualize the Lyapunov. So it's essentially a trial and error method in the nonlinear systems domain. But now in the age of generative AI, maybe you can ask Gemini or ChatGPT to create Lyapunov function for you. And frankly, I have not used Lyapunov function. So for instance, we are talking about this battery example quite a bit in the class. So batteries are driven by partial differential equations. So that's what characterizes the dynamics in a battery. And so I've not seen Lyapunov function in the context of PDEs, but it just could be because I have not read the right references. So I assume that for PDEs, there will be appropriate extensions of this Lyapunov idea to be able to prove that system would be stable or unstable. So a lot of things to read and study, not enough time to go through all of it. Okay, so in my in today's class, my Lyapunov function will be v of x equals to x transpose px, and p is positive definite. So how many of you are aware of positive definite matrices? How many of you have seen it before? 1, 2, 3. Okay. We have 20 enrolled students. We have 7 students in the class, or whatever, 8 students. So I don't know about the other 12 students. So let's just go very quickly over this theory of positive, like what the definition of positive definite matrix is. So you have real, symmetric matrix with all eigenvalues greater than 0. This is called positive definite. So real symmetric matrix with eigenvalues greater than equal to 0, this is called positive semi-definite. Less than 0, negative definite. Less than equal to 0. So this is all eigenvalues. So all eigenvalues have to be positive, have to be non-negative, have to be negative, and have to be non-positive. This is negative semi-definite, and if it is eigenvalues have both positive and negative part, then it is called indefinite. I'm going to use the notation. Well, I'll let you guys write it and then I'll introduce the notation. Let me put the notation here. So I'm going to use the notation p greater than 0, p greater than equal to 0, p less than 0, p less than equal to 0. For positive definite, positive semi-definite, negative definite, and negative semi-definite matrices. For indefinite matrix, there is no notation. Those of you who have taken optimization class must have seen positive definite and positive semi-definite matrices. But in this class, we'll need the notation for negative definite and negative semi-definite as well. So whenever I'm writing a matrix with a greater than equal to 0 greater than sign, it doesn't mean that the elements of the matrices are positive. It means that the matrix is real, it's composed of real values, it is symmetric, and all eigenvalues are greater than 0. Some properties of positive definite matrices, I think you have lambda min. So P is greater than 0, greater than equal to 0, implies lambda min P norm of x square, this is the L2 norm, is less than equal to x transpose px is less than equal to this is a fundamental inequality satisfied by positive definite matrices. It would be the case for negative definite as well, except that the order is going to change in the negative semi-definite case. Okay, any questions so far? Do all of you know why so symmetric matrices are very special class of matrices. So all eigenvalues of real symmetric matrices are real numbers, but they could be positive or negative. So all symmetric matrices are by default, they would lie within this particular space. It could be one of these two. If one of the eigenvalue is equal to 0, then it is positive semi-definite. If all eigenvalues are positive, then it's positive definite, and so on. And then this is the fundamental inequality. This is the inequality that we will need in the rest of the class today. Okay. No further questions. So today I'm going to prove the following result. Let's do one thing. So my V of x equals to x transpose px. My x dot of t equals to a of xt. What is d over dt of v of xt? Okay. Now this is complicated. How would you solve it? Yeah.
I guess would you use the product rule? So it'd be like x dot t times p times x plus xt times p times x dot.
Is this what you were thinking?
Yes.
So I have two terms that are functions of time. So first I'll take the derivative with respect to the first term, and then I'll take derivative with respect to the second term. What do I get? Right? You get this term. So I'm going to write it here. V of x equals to x transpose px, and v dot of xt equals to xt transpose A transpose P plus PA. I'm going to call this matrix C, xt. Once again, I'm overloading the matrix. C was used as an observation matrix earlier, but now I'm using it to denote this matrix. Well, the book uses C. Maybe I'll use G. I don't want to confuse between the observation matrix and the matrix we are using in the class, so I'll just use G. I think G is something that we will not be using later. But the book uses C to denote this matrix. So if you're reading the book, the C matrix is used both as an observation matrix, so yt equals to cxt, as well as A transpose P plus PA. Okay, so what's the theorems that we will talk about in the class? Theorem 4.22 from the book. This says if there exists P greater than 0, I mean P is a positive definite matrix such that G is negative semi-definite, then X equals to 0 is stable. Theorem for 4.24. There exists P greater than 0 such that G is negative definite, then X equals to 0 is exponentially stable. And then theorem 4.26. There exists P symmetric such that G is less than 0, then this is X equals to 0 is unstable. Awesome. These are the three results. The first two results is what I'm going to prove in the class. The result for the third theorem is slightly more complicated, but I'll give you the intuition so that you can go back and read the proof in the book. Okay. So I can pick any P, any positive definite matrix P, but what this theorem is saying that you have to find a P, positive definite P, such that G is negative semi-definite. Okay, so P is symmetric. P is a symmetric matrix. G is by definition symmetric matrix. So P and G here would be symmetric, real and symmetric, just by construction. So P is symmetric by construction and G is automatically symmetric because G is given by this expression. But if P is positive definite and G is negative semi-definite, then it implies that x equals to 0 is stable. If there exists a P greater than 0, so if there is a P which is positive semi-definite, such that G is positive negative definite, then it is exponentially stable. Okay, so it differs only in the sign for the G. So here G can have 0 eigenvalues, here G has to have negative eigenvalues. Now if P is symmetric, so it's indefinite, it's just a symmetric matrix, it could have positive eigenvalues, it could have negative eigenvalues, and G is strictly negative definite, then it becomes an unstable. It becomes an unstable system. Okay. So let's look at the first theorem. So I have my phi t. This is my solution. This is what my solution looks like. So V of phi t equals to so that's the observation number 1. Observation number 2 is okay. Let's take the first derivative. Okay. P beta transpose P. Okay, so what are we doing here? Energy at time t is the initial energy plus the integral of whatever energy has been dissipated / added to the system. Okay, so I'm taking the time derivative and integrating it with respect to d tau from 0 to t. That gives me energy at time t. What about this term here? So g is negative. For our first result, g is negative semi-definite. So this term is less than equal to 0. So at every point of time tau, this term is negative, this term is negative semi-definite. So this entire term is going to be less than equal to 0. That's the property of negative semi-definite matrix. And consequently, what we have is V of V t is less than equal to V of V0. Or alternatively, Vt transpose Vt is less than equal to V of x naught transpose p. X naught this is less than equal to lambda max of p norm of x naught square and this is greater than equal to lambda min of p norm of Vt square. Or in other words, okay, so what are we doing here? I'm writing the value function, the Lyapunov function at time t as Lyapunov function at time 0 plus the time derivative of the Lyapunov function integrated from time 0 to t. Now I know that this particular derivative is non-positive. So it could be equal to 0 or it could be less than 0, right? So consequently, from I'm integrating something that is less than equal to 0. So this entire term, this entire integral is going to be less than equal to 0. Consequently, I get this expression that the potential, the Lyapunov function at time t is less than equal to the Lyapunov function at time 0. I have an upper bound on the time 0 Lyapunov function. I have a lower bound on the Lyapunov function at time t, and I can rearrange this whole expression in this particular fashion. So if x naught for every epsilon greater than 0 such that the entire trajectory is less than epsilon, I can find a delta such that this whole thing is less than epsilon, and therefore this is a stable, x equals to 0 is a stable equilibrium for this particular linear system. So what does this linear system have? If I pick a positive definite, there exists a positive definite matrix such that G is negative semi-definite, then x equals to 0 is stable. So that completes the proof for the stable part. Now we want to prove that it is exponentially stable, and the only change I'm making here is that G is strictly less than 0, right? So now the question is, how do we prove that in fact this decay is going to be exponential? Okay, so we want to get something which is exponentially decaying here, in which case I'm able to prove that this is exponentially stable. So how do I get an exponentially decaying term here? We can just trace the proof right here, and the only change that I have to make is G is negative definite here. G is negative definite. So consequently, I have here something that is strictly less than 0. So I have something that is strictly less than 0. How does that give me exponential decay here? So let's think about it. Any questions on this before I jump on? Yes, please.
So I just had a quick question about
Yes.
the derivative. Are we linearizing that at the equilibrium point, or are we using the nonlinear?
No, right now we are just talking about linear system. So there is no, well, how do you get to a linear system? You try to do take the derivative around the equilibrium point in order to get, not equilibrium point, but equilibrium trajectory in order to get the linear system. So some of that is true, but you want to remain within the bounds of that approximation, right? So you can definitely get out of bounds of that approximation. To give you an example about the flight thing, because you've done the flight dynamics example now. So you have a flight which is going at steady state, right? So the angle of attack would be maybe 5 degrees, 6 degrees, or whatever. The linear system behavior will probably be good enough for 10 angle of attack. 10 to 20 angle of attack, the linear system behavior will be very off. You won't be able to do a good approximation. Above 20, there is no linear system approximation. At that point of time, the system becomes unstable and the flight crashes. And this incident happened for an Air France flight from Brazil to Paris in 2011, where the pilot made the nose up so much that it basically became unstable and it crashed in the ocean, and all the passengers died on board. So the linear system behavior is always within a certain bound of whatever the original nonlinear system is doing. But right now we are just talking about linear system, and we are talking about global equilibrium behavior here, knowing well that some of these are mere approximations and not representative of the actual system in the global sense. Okay. Any other question? Okay. Everything that I have written until now still remains true. The only thing that changes is this one is now negative definite. So I can write it as less than equal to minus gamma I want to make sure that okay, let me write it in the way it's written in the book. So that way I have C1 norm of, I'm using 2 norm here. So whenever I write the norm, it is the 2 norm. This is less than equal to V of Vt less than equal to C2. So this gives me v dot Pt is less than equal to minus C4 over C2. Okay, so by merging this expression and this expression, we are able to arrive at this particular inequality. And this inequality is pretty cool because I have the time derivative of Lyapunov function less than equal to some negative value multiplied by the Lyapunov function itself. Okay, so this type of integral expression is studied under the umbrella of Grunwald's inequality. So what is Grunwald's inequality? So you have if your u, no, u is also taken. I have used x, y, z is not taken. So if I have z dot t is less than equal to beta t zt, then this implies z naught equals to, then this implies that u zt is less than equal to z naught exponential integral 0 to t beta tau deta. This is the result that we will need in order to do the integration here. This is less than equal to, here, less than equal to, less than equal to. Both of these are less than equal to. So the reason it would be, it's sort of, you have this equality in case, I mean, if beta was not time varying, then you have this equality, and this is something that you have studied in your differential equations class. But the cool thing here for Grunwald's inequality is that even with the inequality, this sort of expression holds. And you can check out Wikipedia. Wikipedia has a very nice article on Grunwald's inequality. But the reason I think this inequality is something that we use extensively in dynamical systems. So we are using it in the context of Lyapunov methods, but people use it in all kinds of different problem statements. So this Grunwald's inequality also appears in proving convergence of reinforcement learning algorithms and so on. So it's a very powerful inequality that is used across various classes. Wonderful. So I have a time derivative here, which is less than equal to minus C4 over C2 times. So this is my beta t. It's actually not a function of t at all. And this is my zt, and this is my z dot t. So what do I get from Grunwald's inequality? Any questions so far before I erase the board? Okay. So I have v dot of t, v dot of phi of t is less than equal to minus c4 over c2 v of phi of t. Then Grunwald's inequality implies that v of phi of t is less than equal to v of phi of 0 exponential minus c4 over c2t. This is less than equal to lambda max of p x0 square. So I have lambda min of p norm of phi t square less than equal to lambda max of p norm of x naught square exponential minus c4 over c2t. So this is the exponential decay term. Everything else is a constant. So this implies exponential stability. Okay. Awesome. So, just by a small change in the sign, the fact that G was some eigenvalues of G were 0, all eigenvalues of G is strictly negative, you go from stable system to exponentially stable system, which means that you converge to the equilibrium exponentially fast. If you are in controls area, and if your job is to design a power electronic circuit to do something, or if your job is to make sure that a luxury vehicle works very nicely after going through a road bump, you really are looking for exponential stability in your system, and you will try to design your system in a way that for some positive definite matrix, you get G which is strictly negative negative definite, and that leads to exponential stability. Now let's look at the case where P is symmetric and G is strictly negative. So G being negative just means that the energy that is there in the system is dissipating. Okay, so G being negative definite means you are extracting energy out of the system. So let's see what happens when P is symmetric. Any questions on this exponential stability before I jump on to instability? Okay. Awesome. I'm going to give you a geometric understanding of this, so that way you can read the proof in the book. The proof has a lot of epsilons and deltas, which I don't want to write on the board. Okay, so if P is positive definite, then X transpose Px looks like this. This is my V function. If P is positive semi-definite, then V of X equals to X transpose Px looks something like this. You see there is a direction along which the function is not increasing. Okay, this direction is actually the eigenvector corresponding to 0 eigenvalue of P matrix. Okay, so now let's appeal to the generative AI model in your brain. What happens when P is indefinite? So I have positive eigenvalues, I have zero eigenvalues, and I have negative eigenvalues. Let's consider the case where you have a positive eigenvalue and a negative eigenvalue. What does X transpose Px going to look like? Sorry?
Saddle graph.
Yeah, it's going to look like a saddle point. So how do I show it? I mean, this looks like a Batman symbol, but my goal is not to show, like, give a lecture on Batman, but it's like in one direction it is going down, and in the other direction it is going up. Okay, so it looks like a saddle. Yeah, I'm not able to visualize what a saddle should look like. Maybe I need to work on my generative AI skills in my brain. But this should look like a saddle. So go back and look up Wikipedia or some horse riding website, and you can find saddles there. Okay, there are lots of saddles there. So you can find saddles that. So the idea of a saddle is that along one dimension it is going up, along the other dimension it is going down. And so the place where it is going down is in the direction of eigenvalues corresponding to eigenvectors corresponding to negative eigenvalue of P matrix. Now what's happening in this case is this is where x naught is. So x naught sits at the saddle point, and what happens is no matter where you start, sorry, this is x equilibrium. I'm really sorry. This is x equilibrium. This is your x naught, and you are dissipating energy from the system because G is negative definite. So you are dissipating energy. The Lyapunov function has negative derivative. But what that means is you could be going in this direction. Okay, so you could be going to negative infinity in a specific direction in the V space. So your phi t transpose P phi t goes to negative infinity along some direction, and as a result of which you might be unstable. Your actual phi t might be going to infinity. Okay, so that's what theorem 4.26 is trying to prove in the book. What happens in this case? In this case, you start from x naught, you basically converge to this point. This is your x infinity. In this case, you start from x naught, you converge to the point. This is your x infinity equals to 0. So this is exponentially stable. This is just stable. So you converge here and then you don't move anywhere. Whereas in this case, you go all the way to minus infinity. Rather, the Lyapunov function goes to minus infinity, as a result of which you are unstable. Yes, please.
So can you consider this one as a strong convex, the rightmost one as non-convex, the individual one as?
This one is also convex. This one is strictly convex. So P is positive definite. P is positive semi-definite. So this is convex, but not strictly convex. This is strictly convex. This is non-convex. Okay. Okay. So what have we learned in the class so far? We have learned to characterize stability using Lyapunov's direct method. So I can construct a Lyapunov function such that if this condition holds, then it's stable. If this condition holds, it's exponentially stable. If P is symmetric, then it is unstable. How do you come up with? So the magic here is to be able to come up with this P matrix. So the book has an algorithm to compute P matrix using A. So by looking at A, by looking at the eigen decompositions of A and so on, and doing some sort of similarity transform, you can actually compute P by hand. I'll leave the details to the book. If you are ever in a position where you have to define a P matrix for a given A matrix, you can refer to the book and get a P matrix that allows you to demonstrate stability or exponential stability. But I think the tools are important. which is to understand, to visualize what exactly is happening in this Lyapunov method for proving stability, which is you have an energy function and that energy is decreasing along the trajectory. And what does that decrease in energy mean? So in some case, it means exponential stability. In some case, it means stability. And in some case, it means instability. And the key technique there was Gronwall's inequality. I think Gronwall's inequality is another thing that you should take away home from this lecture, because it's used across a wide range of situations. Of course, linear systems and nonlinear systems is are two areas, but it's also used in proving convergence of algorithms and getting sample complexity bound for algorithms if you are interested in those kind of topics. Okay. Let's turn our attention to the nonlinear system, because there were some questions about nonlinear systems. So we'll talk about linearization and nonlinear systems in a bit. Okay, so I have this system W dot T equals to F of WT, W equilibrium equals to 0. I define this matrix A as gradient WF transpose evaluated at W equilibrium equals to 0, and I define my F of F is the remaining term. So F of, well, this is the residual after linearization. So you can think of it as a second order Taylor series term or something like that. Like, what's the second order term in the Taylor series? That's what this F of xt is it contains. So okay, so now the question is, suppose I know the stability property of A, can I infer that this particular system is stable? So here I'm writing it as a function of x, here I have written as a function of w, but I want to maintain that xt should be equal to wt in this case. Okay, this is just the linearized version of the system, whereas this is the nonlinear version. This is linearized in the first, this is the first order Taylor series term, this is the second order term, and this linearization is valid only in the neighborhood, a small neighborhood of W equilibrium, like I was talking about in the flight example. This is in the vicinity of W equilibrium equals to 0. This is what the term looks like. And so real question here is, if A is Hurwitz, is the system, is x equals to 0 stable? Or exponentially stable? Right, so this was the question I think somebody asked in the class. Did you ask about it? Yeah, yeah. So you asked about it, which is, even if A was Hurwitz, Y dot equals to AT is globally, so if I write Y dot T equals to AYT, this system is globally asymptotically stable, because we just proved that in the previous class, that if A is Hurwitz, then this system is globally asymptotically stable. But I can't really infer the global stability of this particular system. And I know that this system is an approximation of this system only around the equilibrium point. So this one doesn't give you the behavior far away from the equilibrium, it gives you the behavior around the equilibrium point. So this essentially lies in between this, which has a global equilibrium behavior, global asymptotically stable behavior, and this one, which is, I don't know what kind of system that is. I don't know if it is a stable system or not a stable system. Okay, so here is the theorem, which I'll try to see if I can prove in the class today. So if theorem 4.32, if lambda IA, no, real part of lambda IA less than 0 for all I, and F satisfies the following. This is small o of norm of x, if x equal to norm of x, then (4.39). Okay, then x equals to 0 is exponentially stable for w dot t is equal to fwt. It's actually it's a local result, not a global result. So this is not globally exponentially stable. This is locally exponentially stable. So around equilibrium point, this nonlinear system is actually exponentially stable as long as f satisfies this condition, and f has to be continuous Rn to Rn. It's a continuous function of x. So just because A is Hurwitz doesn't mean that the original nonlinear system that you started with is exponentially stable. That wouldn't be the case. But in the neighborhood of W equilibrium, and as long as f is very small, then that is the case. So what does fx equals to O of x means? Small o of norm of x. What this means is limit f of x over norm of x goes to 0 is equal to 0. Okay, this is something like f of x equal to x1 plus epsilon. Or x log x. Maybe x log x will not work, because then if I divide it by x, then it will be log x will go to negative infinity. So yeah, this may not work. But x 1 plus epsilon log x works. So something that works as that's around 1 plus epsilon. So it could be 1.5, it could be 2, it could be 3, it could be 1.27. All of that is fine, but it cannot be 1. Okay, there has to be a positive addition in the exponent. If fx behaves like that, which is mathematically written in this particular fashion, then in that case you have the exponential stability of x equals to 0. Okay, so how do we prove this? Here is the recipe. Again, the book has the proof for this particular result, and it requires a lot of epsilons and deltas. But the idea is, it shows that v dot of xt equals to so v dot of xt is actually strictly negative. That's the core idea here in this particular. So based on all of this assumption and using appropriate epsilons and deltas, it's able to prove that this is true for x in a delta ball around 0, closed delta ball around 0. So this is closed delta ball around x equals to 0 point. So in that particular region, the time derivative of the Lyapunov function is negative, as a result of which you get exponential stability of the trajectory for this, and consequently you get exponential stability of the trajectory for this particular nonlinear system. But it's a local result, because this approximation is only valid locally, and this statement is also valid around x equals to 0. So all of this is, so this delta is constructed somewhat complicated way, but this is all a local result, not a global result. So to some extent, if you know the nonlinear dynamics and you look at this linearized dynamics, and assuming that this term is decaying appropriately around 0, you can establish the exponential stability around the equilibrium point. Okay. So in the next class, I'm going to talk about input-output stability. So right now we talked about the internal stability of the system. So we have the state expression, we have x dot equals to axt. We have characterized under what conditions would this system be stable around the equilibrium point, which in this case is x equals to 0. However, many a times we are only looking at we're not looking at the entire system, we are just looking at the output. Okay, we don't know what's happening inside the system, we are looking at the output. And as long as the input is bounded and output remains bounded, then that's called BIBO stability, bounded input, bounded output stability. So we'll talk about BIBO stability, and maybe I'll go over the proof of this result and BIBO stability and maybe some other topics. So I'll see you guys on Thursday. Have a good evening.